Hello, Mr. Kaladi here. Today we're going to continue our chapter on sequence and series. Yesterday we looked at the arithmetic sequence. Today we're going to look at the geometric sequence. The geometric sequence is a sequence where each term can be found by multiplying the previous one by a constant, a non-zero constant. Remember, the arithmetic sequence was where you're adding a constant, so now we're multiplying a constant. It's also called the geometric progression. So let's just explore this idea a little bit, and we'll use a topic ripped from the headlines. When the novel coronavirus COVID-19 was first tracked in Toronto in March 2020, the daily increase in confirmed cases was 22%, and that's gone down a lot thanks to social distancing. But if you started with something as low as 2 cases, how many cases were present after 30 days? So let's try to map this out. The first thing I'm going to do is try to understand what's happening here. So I have day 1, day 2, day 3. For our intents and purposes, we'll call this U1, U2, my favorite band, U3. Okay, now the first day we had 2 cases. Okay, what about the second day? How many cases did we have? Well, we had, the existing cases on day 2. Right, there's 2 people who are already sick, plus the new cases. Now we know the new cases grow by 22%. So basically I need to take the existing 2 cases that I have, and I have to add 22% of 2. Like that. Now you could just do the math straight, but I'm going to show a little trick that we're going to use here. I'm going to factor out the 2, so I end up with 1 plus 0.22. And so really I'm taking the number 2 and multiplying it by 1.22, which gives me 2.44. So again, it didn't really grow by a full person, but that's the 22% growth. So the quick way of, instead of going 2 times 0.22, okay, it grew by 0.44, and then adding it to 2, it's just as quick to write 2 times 1.22. Okay, so that's from day 1 to day 2. Day 3, it would be the same thing, right? It would be, I guess we could do the same thing. Existing plus new, so that would be 2.44 existing plus 2.44 times 22%. So in other words, again, if I can factor this out, I get 2.44 times 1.22. Or another way of looking at this, well, the 2.44 was really 2 times 1.22. So this is really 2 times 1.22 times 1.22. And that gives me 2.9768. The thing we observe is that each time we increase the day, we're actually multiplying by 1.22, right? This number 2 times 1.22, then I multiply it by 1.22 again. And that's going to continue. Now the question was, how many cases were present after 30 days? So we're talking about day 30 now, U30. So let's do a little note here. For day 30, we want U30. Okay, well that's going to be the number 2, right? That's what we started with. Times 1.22 times 1.22 times 1.22 times ... So we have, this is the initial cases, and then we have to do this 30 times. Oh no, how many times? To get to day 2, we have to do it once. To get to day 3, we have to do it twice. So we actually have to do it 29 times. So essentially we get 2 times 1.22 to the power of 29. So I end up with 2 times 1.22 to the power of 29. And that gives me, 638.947, which is about 638 cases. We actually haven't gotten to, there aren't 639 sick people, there are 638 sick people if I had to round it, because you can't have 0.9 of a person. So it's grown quite a bit in 1 month. It's grown many, many times over from 2. One thing to note then, so when we're looking at, this is a classic geometric sequence. When we look at geometric sequences, again, if the arithmetic sequence is related to linear systems, geometric sequence is related to exponential functions. I mean, this example looks a lot like what we did way back in chapter 1 with exponential functions. And it is, it's very much related. And this is an example of exponential growth. But what we have just discovered is the formula for the geometric sequence general term. To find any term in the sequence, I take the initial and I multiply it by the common ratio to the power of n minus 1. So my sequence is un is equal to u1 times r to the n minus 1. R is called the common ratio. I guess I should label that. This is the common ratio, which is not how much I'm adding, but how much I'm multiplying by. This formula is on your formula sheet, kind of similar to yesterday's. Okay, so, in the above example, how long will it take the number of cases to surpass 1,000? Sorry, not 1,000, 1 million. Okay, well, I have a formula now, right? I have, so I need to find out which term number is a million. So I'm gonna sub in a million. Oops. So I have 1 million is equal to 2 times 1.22 to the power of n. We're going to use an equality right now. We're not going to solve this with an inequality. So we have to figure out when we're going to get a million. So how do I solve a question like this? Again, this chapter in some ways is a way for you to refresh your math skills. And this is an exponential equation, so I have to use some exponential skills. First thing I'm going to do is get rid of the 2. So I'm going to divide both sides by 2. So now I have 500,000 is equal to 1.22 to the power of n. Now, to get rid of the n, I'm going to log both sides. Why did I do that? Well, because log 500,000, this n comes down, so I end up with n log 1.22. To solve this expression now, I end up with n is equal to log 500,000 divided by log 1.22, and that is log 500,000 divided by log 1.22. And we see that to get to a million cases, 65.991, so that's approximately, so it's 65 days. We won't quite be there. We need to actually have 65 days, which is crazy. In 2 months, you'll go from 2 to, so in 2 months, you'll go from 2 cases to a million. So you can see why coronavirus is so dangerous at first with that 22% growth rate. We had to have that social distancing to get that, that growth rate down. As we said when we studied exponents, exponential growth is really hard for humans to understand because it grows so quickly. Okay, so let's apply this formula. Anyways, that was a bit of a review of how to do solve exponents using logs. But let's use this general term formula and look at some easy examples of geometric sequences. Okay, first one, 2, 10, 50, 250. Okay, we need to figure out how much it's growing each time. What's the common ratio, R? Well, the way I can figure this out is I take, if you can't just see it, you take the one term and you divide by the previous term. This gives you 5. Similar here, you get 50 divided by 10. It's still 5. So each time it's being multiplied by 5. I'm just gonna make a simple little note there. Find the common ratio by dividing a term by the previous term. So now if I want to use my formula, okay, well, to find the general term, so that is any term, I would take the initial term, which is 2, and I would multiply it by, what was my thing here? General term, which is 5 to the power of n. So common ratio to the power of 5, common ratio r 5 to the power of n minus 1. So that's my general term now. I can use this formula to find any unknown term. In this case, the question wants to know what's u6. So I'm going to sub in n equals 6. So I end up with u6 is equal to 2 times 5 to the power of 6 minus 1, which is 5. That's something I can do with my calculator. 5 to the power of 5, which is a big number, times 2. So you can see, again, this is exponential growth. You can see how fast a geometric sequence grows. This one's multiplying by 5 each time. Very soon it gets out of control. Let's do another example here. Let's keep falling back on this strategy for finding the r value. So here I have r is equal to 20 divided by 40, which is 1/2. And this is the same thing. It's multiplied by 1/2. Each time it's multiplied by 1/2. It's useful to use this strategy for finding the common ratio so you don't get confused. It's not being multiplied by a big number, it's being multiplied by a small number, so the sequence is shrinking. Now I can write out my general term. Un is equal to the initial value, 40, times the common ratio 1/2 to the power of n minus 1. Now, if I want to know the 12th term, I sub in n equals 12, so I have u12 is equal to 40 times 1/2 to the power of 11. I'm going to use a calculator to do this. 0.5 to the power of 11 times 40. Get a very, very small number. 3 significant figures. Does this make sense? Yes, because each time it's halving itself. And you can see how a geometric sequence that has a r value greater than 1 explodes, it gets bigger. A geometric sequence that has an r value smaller than 1 shrinks. And that's something to maybe note. So a geometric sequence with absolute value r greater than 1 grows, while one with r less than 1 gets smaller. At least the values get smaller. That's a little thing to note because we'll be coming back to that in a few lessons. Let's continue. Continuamos. Here we have question C. Okay, same thing. Oh, the numbers are getting scarier, but I can find my common difference the exact same way. R is equal to the term, negative 1/4, divided by 1/2. Now, that's a little confusing. You could write this as negative 1/4 divided by 1/2 like that. We know that dividing by a fraction is actually multiplying by the reciprocal. So that gives me negative 2/4 or negative 1/2. So I would assume this is the same thing. This is being multiplied by negative 1/2, etc., etc., etc. So un, the general term, is equal to the initial term times negative 1/2 to the power of n minus 1. So just because it's the common ratio r is negative, it's not a problem. I can still use it. Now, if I want to figure out what u9 is, I sub in 9, so that gives me to the power of 8. So I have negative 0.5 to the power of 8 times 0.5. You get this very small number. Now let's do this one the old-fashioned way. This gives me half. A negative half to the power of 8 means it's negative times negative times negative. It's always going to be a positive because you have an even exponent. And 2 to the power of 8 is 256. So I end up with 1 over 256. So I end up with 1 over 512. It's a positive number. And this makes sense. As you see, it alternates. When you have that negative r value, the terms alternate plus minus, plus minus, plus minus. So the 8th term will be positive. All the even terms. Right, oh sorry, it's an odd term. U9, so all the odd terms tend to be positive. Let's do one more example. What's happening here? Well, to go from here to here, you could do the division if you want, or you could say, okay, I'm multiplying this by 2x. I'm multiplying this one by 2x. So here, in this case, the r value has a variable in it. It's no matter though. The general term is going to be 7x times 2x to the power of n minus 1. So if you want to sub in n equals 8, you end up with u8 is equal to 7x times 2x to the power of 7. So that gives me 7x times 2 to the 7 times x to the 7. So you end up with 7 times 2 to the 7. So you get 896, and you end up with x to the power of 1 times x to the power of 7. So you add those exponents and you get x to the power of 8. Okay, let's do a more difficult problem. Here we have a geometric sequence where I have u2 and u5 are known. So this is kind of like what we did in our last lesson, except in this case it's a geometric sequence. So I can again try to understand this a little bit. So I have -6, which is my u2, yeah. And then u3 I don't know, u4 I don't know, u5 I do know, that is 162. So I'm multiplying, it's geometric, so I know that there's some sort of common ratio. Every time they go up, I'm multiplying by this common ratio. So essentially what I know is that u2 times r times r times r, so times r to the power of 3 is going to give me u5. So that would be -6 times r3 is equal to 162. So I divide both sides by -6. So I get 162 divided by 6. I get -27. So I need to do the cube root of 27, or what number times itself gives me -27. Well, it has to be -3. -3 times -3 is 9, times -3 is -27. Perfect. So now I know what the common ratio is. I can't quite use my geometric sequence formula because I don't know what the initial value is. I know only u2. So I have to do another expression to help figure out what the initial term is. Find the initial term. So that's going to be, well, I know the relationship between u2 and u1. If u1 is here, I know that r is equal to u2 over u1. So I have -3 is equal to -6 over u1. That gives me -3 u1 is equal to -6. That gives me u1 is equal to 2. So therefore, un is equal to 2, the initial term, times -3 to the power of n minus 1. And you could test it out if you weren't sure. Okay, and now finally, let's do a hard example. I call it a hard example because it is a word problem. And as I said at the beginning, geometric sequences are linked to population growth. So anytime you're looking at population growth, a bacteria population, even a viral population, it tends to follow a geometric sequence, which is also related to exponential growth. So in 2015, the population of the GTA of the Greater Tokyo area in Japan was 13.491 million people. The next year in 2016, 405,000 people moved out of the city, while 405,000 moved in, 331,000 moved out. What is the net increase in the population of the city? Well, that word net, you see that? Net population would mean kind of when you consider how many people move out and how many people move in. So great news, I had 405,000 move in, but then you have to consider the 331,000 who moved out. So when we do the math there, we end up with 405, 1, 2, 3 minus 331,000. So we end up with 74,000. Because that's positive, it's a net increase. It's actually getting larger, but not that larger, right? Because some people are moving out to the countryside. Okay, calculate the annual population growth rate. Well, we know that we can assume here every year 74,000 people come into the, or new people come into the city, the net increase. So if I want to express that as a percentage or population growth, I'm going to take the number of people, 7 that come in, so the change, the net change over the population. So that would be 74,000 over the 13,491,000. So I express that as a percentage. Did it ask for a percentage? Annual population rate times 100%. So that's going to give me 74,000 divided by 13,491,000. So that gives me a number of 5, so 0.005. If I want to turn that into a percentage, I would multiply by 100. So I get 0.5485% or 0.005485. So you can express it as a percent or as a just a decimal. Okay, so assuming the growth rate stays the same, find the general formula for the population. So again, when you were thinking population growth, you should be thinking exponential or geometric sequence. So let's see if we can map this out. We have 2015 is my first year. Let's call that U1. And that has a population of, let me write that in red so we can kind of differentiate it. So in the year 2015, U1, my first term, my population is 13,491,000. Now, the next year, 2016, U2, my population has grown, right? It's the population times the rate. Or, sorry, I should say population plus net increase. So essentially what it becomes is 13,491,000 plus 0.05485 times 13,491,000. Right, so this was the population plus the amount of the increase, which we know is 74,000. But again, what I showed you at the beginning is what you could do is take the population, factor that out, so then you get 1 plus 0. Oh, I wrote this out poorly and forgot a 0. So essentially, a quick way of doing this calculation is to take the current population and multiply it by 1 0.00 by the growth rate plus 1. And that's exactly what we did in that coronavirus example at the start. So I end up with plus 1 times 13,491,000. 20 million. So let me do that. 1.005485 times 13,491, 1, 2, 3. And there we go. I get 13,564,998. When I go to 2017, U3, that's going to be similar, right? It's going to be 13,491,000 times 1.005485 times it again to get that growth again. So each time I do this, I'm multiplying by a common ratio of 1.005485. R is equal to 1.005485. So then, so therefore, if this is a geometric sequence, I can use my formula. My starting term, so what would I say? The general term, so say population is equal to 13,491,000 times 1.005485 to the power of t, where t is years after 2015. Oops, there it is. There's my formula. So my last question, estimate the population of Tokyo in 2025. Well, in 2025, that is 10 years after, so I'm going to sub in t equals 10. So I end up with p is equal to 13,491,000 times 1.005485 to the power of 10. I'm going to use my calculator to do this. 13,491,000 times 1.005485 to the power of 10. That gives me an answer. Did I take that right? 13,491 times. Good. And so I get 14,249,500 and I guess I should round that. I'll round it up to approximately 516 people. Is that number accurate? Well, provided the growth rate, doesn't change, doesn't really include. This is the number of people that move in and move out. Might be forgetting some other things like how many people are born and how many people are dying. So that's another thing that should be in the growth rate. But for this question, according to our model, at least we were able to get a value. So your homework is page 168, number 1, page 169, number 1 to 6, and page 183, number 6, 7, and 10. Those are the word problems, so I do think you should do the word problems because this is there's an emphasis now in the new curriculum to have word problems about things like this. And I would do these trickier problems here. So if you're not going to do everything, those are the ones I would focus on. Good luck with that, and I'll see you next time.